we're going to look at the frequency response of an op-amp with negative feedback in this video. Now we're going to use as an example here the non-inverting amplifier, which we've already seen before, and we've gone through and we've derived the function here that defines the gain of that op-amp. Okay, so I won't talk through that again. You've seen it before and you can read through it again, and you could go and derive it again yourself if you want, or have a look at the previous videos. Okay, now the thing about this here is that we've got the gain of this little network here, but it's only the gain, and the gain's not got any frequency dependence, so we don't really know what the frequency response is of this network. So we can rewrite the gain in this form here. So all I've done is taken the common denominator R2 here, so that's going to be R1 plus R2. So as again, it doesn't tell us how the gain varies with frequencies. Okay, we have already seen, of course, that a compensated op-amp is going to look like a low pass filter. So we know an actual op-amp with an open loop op-amp is just going to look like a low pass filter. So the low pass filter here, the transfer function is going to be g of s is 1 upon 1 plus src. So what we can do is we can rewrite that there as rc is equal to 1 upon omega c, because we derived this little equation there for the cutoff frequency. So it means that if we were to replace the value s with our actual frequency j omega, then we would have a g of j omega equals 1 upon 1 plus j omega upon omega c. Okay, now a thing to remember here is that we're actually dealing with an active circuit. Okay, so there's actually a gain involved in it. So although that is the transfer function for a low pass filter without any gain, but as we say that this constant here in that case would just be 1, but because there is actually a gain in the system, then the gain in the system is actually the constant, so that one there is going to be replaced by the open loop gain, or the DC gain of the op-amp. So we can say then that the open loop gain is going to be equal to the open loop gain DC upon 1 plus j omega upon omega c. Now another thing we'll do here is we'll let that omega c, we'll call it tau for the moment. Okay, so say tau equals 1 upon omega c. So it means just to make it a bit simpler whenever we go and do the algebra. So it means that we're in a position now to start looking at what the actual frequency response is of this network, because we can rewrite this out, because we know that from the op-amp we've got V out is equal to the gain times V in plus minus V in minus. That's just the op-amp. Okay, now we know that the V in minus, which in this case here is equal to the V out R2 upon R1 plus R2. Okay, so we just derived that just in the last page. But where we we slipped up, or where we didn't take account of the frequency response, was in the part of the gain here, because we assumed that gain was just a number, say like 100,000, but the gain isn't just the number. The gain's got to be frequency dependent. Okay, so and we've just seen that this here is the frequency dependence of this gain, so we don't just have a number for this, we actually have that function there, which is a transfer function, in to multiply out these. Okay, so it means if we put this in here, we're going to get this line here. Now I'm not going to go through all of the algebra because it's a bit kind of tedious, and I can leave it up to yourself, but you can multiply these out and multiply that end out, and then you can gather the like terms, and you can get it in terms of V out upon V in, and when you do that you're going to be left with R1 plus R2 upon R2 equals this part of the equation here. Now this here is the actual transfer function of that circuit with negative feedback. So it's a frequency dependent gain. And you can see there, this here, it still just looks like a low pass filter because we've just got a gain section here, K, and if we replace this here, whole point here with tau dash, then we could just have 1 upon 1 plus j omega tau dash, and you can see there that this thing here is just the low pass filter. So really what we're saying is at lower frequencies, the gain of this network is really dependent on the resistors R1 and R2, and you can see the resistors R1 and R2 in here. So it means that the gain of this op-amp network is not really dependent on the gain of the op-amp, it's dependent on the external resistors only, and that's what we expect to see with our op-amp, and we've seen it on the previous designs that we've been doing. Okay, now we're going to look at the same bit of information, but we'll look at it in terms of the frequency at a much higher frequency. Okay, so we'll look at it at the frequency when the gain is equal to 1, which is the unity gain point. So what we can look for is the magnitude of our gain, and we say our magnitude of our gain in that point is going to be at the unity gain is going to be equal to 1. Okay, so we're just saying that we're looking at the frequency at which the gain goes to 1. So the magnitude of the gain is equal to 1, and that there is the equation that we've just derived, which gives us the gain with respect to frequency. Now what we're going to do is we're going to find the magnitude of that. Okay, so that's a constant term, and we're going to find the magnitude of this section here. So what we can do is we can multiply up by, in fact what we do is if we multiply up by R1 and divide by R1 plus R2, then we'll end up with R1 upon R1 plus R2 at this side. Okay, and then we can take the reciprocal of both sides, so the reciprocal of this part here just becomes 1 plus this section, and of course the reciprocal of this side here is just going to go back to R1 plus R2 upon R2. Okay, so work through that a little bit and convince yourself of that. Also the magnitude of this section here, well, if we ignore that value of 1, it's just going to be the square root of this section here squared, which is just going to give us our R1 plus R2 upon the g omega LDCR2 times omega tau. Okay, so it's just this section here. So this whole thing here is going to equal our R1 plus R2 upon R2. So if we can cancel out our R2s here with our R2 and our R1 plus R2 with R1 plus R2 there, and then we can take up the value of our keep our value of omega here. So this will be our omega at a unity gain. That's going to equal the open loop gain at DC times our value of tau, 1 upon tau, which 1 upon tau is just equal to our omega c. Okay, so it means that the unity gain then for this circuit with negative feedback is just the open loop gain at DC of the op-amp times the value of omega c. Now that there is just the same unity gain equation for the op-amp that we derived in one of the previous videos. Okay, so really all we're saying is that at high frequencies the gain of this circuit with negative feedback just looks like the gain of the op-amp. Okay, so basically saying the op-amp takes over the frequency response, and that's kind of what you would expect, and I've got it drawn down here. So if we had the frequency response of the actual op-amp in blue here, and we had in pink the frequency response of our circuit, then at low frequencies you can see, as we've seen derived earlier, the gain is determined by the values of the feedback and the feed forward resistors. So the gain's determined by the external resistors and not by the gain of the op-amp. But at high frequencies, as we've just seen here, the gain is dependent on the actual op-amp. So that means that the transfer function for this circuit here would be controlled by the resistors at low frequencies, but controlled by the op-amp at high frequencies. So that's all there is to this video, and I'll get you in the next video. Goodbye.